So we've finally reached our mathematical part of acids and bases. We've been talking about pH and what it means in terms of relative concentrations, that each point on the pH scale is 10 times difference in concentration. But now we're actually going to start looking at some of the calculations we need to do in order to be able to properly quantify the concentration of hydronium ions. So if we think about water, we've talked about the fact that water can ionize in solution, that we can have two molecules of water, and when they come in to interact with each other, we can form H3O plus and OH minus. Okay, so this is what we mean by the self-ionization of water here. So we can actually quantify how much that will happen at particular temperatures. And what we do is we refer to that as the ionization constant, and we give it this Kw. We'll learn more about K when we do equilibrium, but for now, this is the key thing that we need to know, that the ionization constant of water is equal to the concentration of the hydronium ions multiplied by the concentration of OH minus. This is a temperature dependent value. Okay, so at different temperatures it will be a different value, and the one we use is for standard conditions, which is at 25 degrees C. Okay, so we can use this in water and also any aqueous solution. Sometimes you'll see it referred to as the ionic product constant, but really we just refer to it as the ionization constant, or Kw. At 25 degrees C, which is our standard conditions, not standard temperature and pressure, standard conditions, so 298 Kelvin, both the concentration of H3O plus and OH minus is the same. Okay, this is for pure water. So the concentration of H3O plus and OH minus is the same, meaning it's a neutral solution. And if we actually measure the concentration of each, we will find that it's 1 times 10 to the negative 7 molar, or 1 times 10 to the negative 7 moles per decimeter cubed. Okay, which means that we can write that Kw is equal to the concentration of H3O plus multiplied by the concentration of OH minus. Because they're the same, they're going to be the same value. When we multiply these values together, we just add together the indices, and what we get is this value here, which is 1 times 10 to the negative 14 moles per litre squared. Okay, so we don't need to worry about the units yet. As I said, we'll talk about that a little bit more when we do equilibrium, but we do need to know this expression here. Okay, you're actually given the value for Kw in your data booklet, but it's a really handy one just to have memorized so you can use it easily. What that means, okay, is that in acidic solution, the hydronium ions, okay, are formed when we add extra acid into the solution, as well as the self-ionization. So if we have hydronium happening because of the self-ionization of water, forming our hydronium ions and OH minus, when I add in an acid such as HCl into water, what I'm going to see is I'm forming H3O plus and Cl minus. So now I have an additional quantity of H3O plus. So I'm going to drive the concentration of H3O plus up, which means that the concentration of H3O plus is going to be greater than 10 to the negative 7 molar for an acid. Okay, and correspondingly, the concentration of OH minus is going to be less than that. Okay, so now that I've scribbled all over our summary here, let's have a look at our summary. So at 25 degrees C, pure water in neutral solutions, the concentration of hydronium ions is equal to the concentration of H3O plus. Okay, which is 10 to the negative 7 molar. In acidic solutions, it's going to be greater than, and the OH minus concentration will be less. In basic solutions, our OH minus concentration is going to be greater than our H3O plus. That should already align with what you know about acids and bases. Higher concentration of OH minus, we've got a base. Higher concentration of H3O plus, we have an acid. When they're equal, they're neutral solutions. We've just added a numerical value to that now. So for concentrations of H3O plus, okay, they range from 10 to the negative 14 molar for strongly basic to 10 molar for concentrated strong acids. And 10 molar is the strongest concentration of HCl or sulfuric acid that we can get, and we refer to that as concentrated, or conc for short. Indicators that change colour can be used to measure the difference in acidity of that, and we've seen that already. Okay, but because the pH scale has such a large range, that's why we find that it's that times 10 difference in concentration. This brings us to a couple of equations. So this is our self-ionization and constant of water. We've got that, and that is equal to 1 times 10 to the negative 14. Okay. The other one that we have is, because the pH scale is a times 10 difference between each one, essentially what we've done is created a scale, a logarithmic scale, which means that we can calculate our pH by using the log to base 10. For pH, the formula that we need to know, okay, and yes, you need to know it, is the pH is equal to the negative log to the base 10 of the molar concentration of H3O+. That means that pH can only ever be calculated based on the concentration of H3O+ or H+. Okay, we can rearrange that log equation to give us that the concentration of H3O+ is equal to 1 times 10 to the pH. Okay, so now we can figure out our pH from that as well. This pH is equal to the negative log to base 10, though, is the one we use most of the time. This is just a summary of that and relating it back to our pH scale. Okay, so for pHs that are equal to 7, okay, we have negative log to base 10 of 10 to the negative 7, because remember H3O+ concentration was 10 to the negative 7. And then we're going to have the same being able to be plugged in for our acid and base solutions. Let's have a look at this sample problem here. Okay, what it's asking us to do is calculate the concentration of hydrogen ions, so hydronium, in blood if the pH is 7.4. So we know that our pH is equal to 7.4. Okay, which means that now ionization constant isn't going to help me, because that's just concentrations at 25 degrees. My pH is equal to the negative log to base 10 of the concentration of hydronium is where I'm going. But in this case, I want to find out the concentration of H3O+. So we can remember that it was 1 times 10 to the negative pH. Okay, so in this case, now I can say that if my pH is 7.4, okay, then that means that my concentration is going to be equal to 1 times 10 to the negative 7.4. Okay, and I can put that in my calculator. 1 times 10 to the negative 7.4, and what I get is 0.00012344. So I get this 4 times 10 to the negative 8. Okay, so this is just we need to remember this form of the equation, substitute it in, and then what we get is 4 times 10 to the negative 8, because this will be 1, 2, 3, 4, 5, 6, 7, 8 for my scientific notation. So we get 4 times 10 to the negative 8 molar. So if pH of blood is 7.4, then we have quite a small number of hydronium ions in solution. Let's look at sample problem 2. So this is looking at it a different way. Okay, in this case, we have 40 mils of 0.2 molar hydrochloric acid, okay, and we're reacting it with 20 mils of 0.1 molar sodium hydroxide. And we've been asked to calculate the pH. Here's the thing. This time round, we have a reaction occurring. Hopefully you can see that it is an acid and base neutralization reaction, and that reaction is going to be HCl plus NaOH is going to give me a salt, which will be sodium chloride, and water. Okay, this is a monoprotic acid. It's going to give up 1H plus. Sodium hydroxide will give up 1 OH minus. Now I can work through my calculations and therefore work out the amount of sodium hydroxide that will react with my hydrochloric acid. And if we look at the solution that we have here, that way we don't have to work on my dodgy pen work on my computer. Okay, we can see that we have our equation. Okay, then this piece of information here, remembering that the reaction between strong acids and strong bases is virtually complete. So we'll get ionization. The HCl will completely ionize. The sodium hydroxide will completely ionize. So now I can work out the number of mole of HCl using my concentration times my volume. My concentration coming from up here, and then my volume, remembering to convert that through to decimeters cubed. Okay, so now I have my concentration multiplied by my volume in decimeters cubed, which gives me 0.008 mole of HCl. When I have a look at my sodium hydroxide, we do the same thing. We have the molar concentration of my sodium hydroxide multiplied by the volume in decimeters cubed, gives us 0.002 moles of sodium hydroxide. Hopefully you can realize from this, if it's a 1:1, we have a situation where we have limiting in excess. Okay, because 1 mole of HCl is going to react with 1 mole of sodium hydroxide. We can see straight away here that our sodium hydroxide is going to be the limiting factor. So this means that only 0.002 mole of HCl will react. I can work out how much remains unreacted by taking the initial number of mole of HCl, subtracting the number of mole of HCl that will react from that, and this leaves me the number of mole of HCl that is forming hydronium ions in my solution still. So this essentially means that if all the rest of it has neutralized, this is what's going to contribute to my overall pH. Because HCl gives 1 mole of H3O plus, then the number of mole of H3O plus is going to be equal to the number of mole of hydrochloric acid, as a 1:1 ratio. And then now to work out the concentration, we need to know the total volume. We added 2 solutions together. One was 40 mils and one was 20 mils, which means my total volume of solution, okay, the total volume is going to be 60 milliliters. That means that I need to convert this into decimeters cubed when I do my final calculation for my concentration. So I get my number of mole divided by my volume, and I get that the molar concentration of H3O plus is 0.1. Now I have my concentration of H3O plus, I can start to work out my pH. Hopefully you remember that pH is equal to the negative log to base 10 of the concentration of H3O plus, which I now have over here. We can substitute that into the equation and we get that the pH of the solution after the reaction will be 1. Have a pause, go through it yourself, see if you can follow the calculations before we move on to the last example of how we work out pH, which is sample problem 3. Okay, hopefully you figured out your volume stoichiometry and how we substitute that into our pH calculation from the previous question. Now I'm going to look at something where we've been given the concentrations of a base, remembering that the concentration of H3O plus is the only thing that determines our pH. So if it goes up, it's an acid. If it goes down, it's a base. Okay. In this case, we now have only been given the concentration of our base, and we need to work out the concentration of those solutions. This is where we're going to use that Kw, okay? Kw is equal to 1 times 10 to the negative 14, which is equal to the concentration of H3O plus times the concentration of OH minus. Hopefully you can see from this, by using that, if I have that the concentration of H3O plus times the concentration of OH minus is equal to 1 times 10 to the negative 14, that means that anytime I'm given a concentration of OH minus, I can find the concentration of H3O plus by taking 1 times 10 to the negative 14. Okay, keeping that all in brackets in my calculator, and dividing by the concentration of OH minus, again remembering to keep everything in there on the denominator in brackets when I use my calculator. Then from there I can input this value in to the pH is equal to negative log to base 10 of the concentration of H3O plus. So let's have a look at this work solution. For the first one, we've been given sodium hydroxide concentration, and we can see that sodium hydroxide will generate 1 OH minus when it ionizes in water, which means that the concentration of sodium hydroxide that we were provided in the question is going to be equal to the concentration of OH minus. Okay, so I can now substitute this into this equation here. Or the other thing, this is another tricky way that we can do it. Okay, so I can follow this process where I substitute in and find the concentration of H3O plus, or I can use the fact that the pH is equal to 14 minus the POH. So this is an alternative method which requires you to do a little less manipulation. Okay, which means that the pH is going to equal 14 minus negative log to base 10 of the concentration of OH minus, because that's what our pH is. And if that's the way they've done it over here, so it's negative log to base 10 of the 3.34 times 10 to the negative 5, which is equal to 4.48. 14 minus 4.48 is equal to 9.52. I'd like you to have a go pausing it and trying to do it using the method up the top, and then you can decide which one you prefer. For number B, okay, this time we are looking at the fact that magnesium hydroxide will produce a 2:1 ratio. So we'll get 2 OH minus ions for every magnesium, every magnesium hydroxide. Okay, so in this case we're going to double the concentration of magnesium hydroxide to form the concentration of OH minus. Find the POH by putting in the negative log to base 10 of the concentration of hydroxide ions, and then subtract 14 minus POH is going to give me a pH of 10.7, which means that our solution is basic. Have a go at reading through those again. Hopefully you'll follow them, and we'll do some more sample calculations in class. I've got a couple of worksheets for you to practice these.